There we go. So without further ado, Jonathan Payne on connecting end-Permian paleontological and geochemical records using physiology and Earth system models. Jonathan?
Thanks so much for the kind introduction, Jim. Before I get started, one quick question so that I use our time well. When would you like me to be done speaking so we make sure we have time for questions and don't keep people too late?
Let's shoot for about 8 p.m., which would be 50 minutes from now.
Okay, so questions will start at 8 o'clock.
That's correct.
Or
yeah.
Okay.
And again, I'll handle questions coming from the chat at that time, and we'll also have the ability for people online or in the room if they want to come up and use the microphone here to speak to you at that time as well.
Okay, sounds great. Thanks so much. And again, thank you for the invitation to speak. I'm sorry that I wasn't able to come in person. The life of a senior associate dean with kids at home doesn't leave lots of gaps in the schedule, I'm learning. But you know, I hope that I can end your day by talking about one of the worst things that's happened on the planet in the last 500 million years. And you know, I find it very interesting, and I hope you will too. I think, you know, I hope you'll also see some of the relevance to the world that we're facing at the moment. And I hope that we can, as geologists, offer a unique perspective in terms of the temporal and spatial scale at which we see how the Earth system works. Let's see. So I wanted to start off by mentioning the fact, which I imagine everyone in the room knows, which is that, you know, when you go and give a talk on scientific research, especially when you're 20 some years into your career, you're not presenting stuff you've done on your own. You're presenting research that's been done with and by graduate students, postdocs, and collaborators from all around the world. I don't have time to introduce everyone on my acknowledgement slide, but I will point out, you know, we've worked on parts of our project with groups of high school interns, pictured over here. I've benefited enormously from the generosity of a couple of Chinese colleagues who have hosted me on multiple, you know, many week to many month field seasons in China, collaborators in Turkey, and many from around the U.S. and so this talk represents you know, a synthesis of the research done by all of us working together. And I wanted to just start by you know, making the case for geology as a useful discipline in the study of Earth system change. And I like to start out with this when I teach introductory historical geology as well. Because I think, you know, we often start with Charles Lyell and the principle that the present is the key to the past, right? That we use processes that we see happening today in order to interpret the structures that we see in the geological record. And of course, this has been incredibly successful, right? This type of reasoning is most of how we're able to interpret the geological record. But if we back up even a little bit farther in the history of modern geology to James Hutton, the Scottish geologist who predated Lyell in the late 18th century, his project in geology was actually, I think, a little bit more radical than Lyell's in many ways, which is that he really felt that by looking back into the geological record, we could project forward geological processes into the future in a way that you couldn't if you only looked at present day processes. And so I pulled out this one passage, which I hope you'll enjoy, which is from his theory of the Earth. And he said, and he's standing on the coast in Scotland, right, and looking out at some sea stacks and thinking about how erosion works. And so he says, we advance with some degree of certainty into the annals of a continent which does not now appear. And in tracing those operations which are past, we foresee distant events in the course of things. We see the destruction of a high island and the formation of a low one. And from those portions of the high land or continent, which remain as yet upon the coast and in the sea, we may perceive the future destruction, not of the little island only, which has been saved from the wreck of so much land, but also of the continent itself, which is in time to disappear. Right. And so we see both the Lyellian part of this, right, which is that I see erosion happening today at the coast. And so I understand how these sea stacks formed from the erosion of small islands or from the erosion off of the coast of the mainland. But what he finds exciting about this, I think, is not that aspect of geology, but in fact, it's his ability now to imagine what the world will look like many centuries, many millennia, many millions of years after he's gone, right? That from understanding these geological processes, he sees this future of how islands and continents will erode. In the modern day, we understand that continents don't actually get completely destroyed by erosion. But I think the point stands here that Hutton is really thinking about the future as he's doing geology, just as much as he's thinking about understanding Earth's past. And I certainly hadn't appreciated that, I don't think, early in my geological career. But as I was digging around for ways to talk about why geology matters for people in a school of sustainability, for example, especially for those of us doing deep time Earth history, as opposed to those of us saying doing hydrogeology, climate work, resource related work. And to me, it really boils down to that one phrase in here, that in tracing those operations which are past, we foresee distant events in the course of things, right? And we know as geologists that we can't linearly extrapolate the processes we see happening today deep into the future. In fact, very little extrapolates linearly. And so the geological record is very important for us to understand how processes play out at different timescales over many orders of magnitude. Okay, so let's jump into the end-Permian. So, for this audience, I think everybody knows that there have been 5 major mass extinction events in the history of animal life on Earth. Animals first appeared on the planet a little more than 600 million years ago in Ediacaran time. For those of you who aren't paleontologists, one of the really exciting developments in paleontology over the last decade or two has been much more sophisticated interpretation of these early animals. For our project today, the key thing to know is that animals increased in diversity, plateaued during the Paleozoic, interrupted by a couple of mass extinction events in the Ordovician and Devonian, then were walloped at the end of the Permian, hit again at the end of the Triassic, and then, of course, I imagine everyone here is well familiar with the end Cretaceous mass extinction. And those mass extinction events really stand out as peaks in extinction intensity. In principle, a biologist could argue with you that, if you see a drop in diversity, maybe it's that origination rates dropped rather than extinction rates increasing. By looking directly at the geological record, it's very clear that extinction events, that these diversity declines represent extinction events. And there's been lots of ink spilled in the technical literature on whether these mass extinction events are statistical outliers relative to the background distribution. There are some reasonable arguments on both sides. I think the geological record shows that there are fairly distinct mechanisms that occur during these major mass extinction events that don't occur at other times. So the processes governing them are a bit different from background time. And the end-Permian was certainly the most severe of these biotic crises. And we've learned a lot over the last couple of decades about why the end-Permian extinction event happened and how it affected the history of animal life. And so that's what I wanted to talk about today, is that we're getting much better at connecting the geological and geochemical evidence that we have for bad things happening with the paleontological evidence that we have of taxa going extinct. And my hope is that I can convince you by the end that we're able to do some things with climate models and with data from animal physiology experiments to really start to connect these two fields together in a way that was hard to do previously. So when we look at the end-Permian extinction, one of the things that's happened in the last decade or two is that we have much better geochronology on the extinction event. And so these are data on the left. This is a paper published about a decade ago by Shen-Shu Zhang and colleagues from Nanjing in China. And by compiling data from a number of different stratigraphic sections across South China and using some statistical algorithms to bring those data sets together, and then pinning in radiometrically dated volcanic ash layers, they were able to establish the pattern and timescale of this end-Permian extinction, showing that even in the last few 100,000 to million years before the end-Permian mass extinction, there was no gradual decline in diversity. Diversity was quite stable. And then over an interval, if we look carefully, that spans, let's say maybe at most 200,000 years, we get this very dramatic decline in diversity. So this is much shorter than a geological stage. In the best studied regions, it plays out over a couple of beds of stratigraphy. And in fact, since this 2011 paper, there have been repeated efforts to redate these ash beds using, taking advantage of advances in zircon preparation to reduce the effects of lead loss. And that every time we do that, the extinction interval seems to get shorter. And so in this 2014 paper by Seth Burgess and colleagues, the extinction interval between beds 25 and 28 comes down to on the order of 60,000 years, which, as you can see, is only slightly larger than the analytical error on the ages of these ash beds to begin with. And so we're looking at an extinction event that was geologically very rapid, potentially resembling the timescale of anthropogenic extinction, particularly given that we can start to trace human impact on terrestrial faunas back 100,000 years already, right? And so this extinction event is not terribly different in timescale from the extinction event that we're experiencing at the moment. So that part, is really, hats off to the geochronologists and field geologists for tracking down all these ash beds and doing the heroic work of separating individual zircons and getting their ages by isotope dilution TIMS. At the same time, we've had some real insights, I think, from the paleontological record that have started to reveal to us what's interesting about the end-Permian extinction. And this is what brought me to grad school, was Andy Knoll working on this problem. And the figure on the left is a figure from one of Andy's later papers on this topic. But he and some collaborators were the first to point out that there's a major taxonomic selectivity to the end-Permian extinction, and that taxonomic selectivity relates to animal anatomy. And so many of you who were undergraduate geology majors probably learned something about the fact that at the end-Permian extinction, rugose and tabulate corals went entirely extinct. Brachiopods were decimated, right? The brachiopods are mostly they're the most common shell that you find in Paleozoic rocks. Bivalves and gastropods become the most common shells afterward. That's the end-Permian extinction. And what we see is that Andy pointed out that if we think about what's different between these groups, the groups that were most heavily hit by extinction were the groups that had heavy calcium carbonate skeletons and less developed respiratory and circulatory systems. The groups that did all right, much better than those heavily calcified corals and brachiopods and crinoids. So these are the clams and snails. They experienced 50% extinction, which is sort of end Cretaceous level extinction, but not as bad as the heavily calcified groups. So these groups tend to have more sophisticated respiratory and circulatory systems. They're actually less calcified relative to their biomass. And then when we go over to the groups of organisms that don't have calcium carbonate skeletons, they survived much better. In fairness, they also don't have great fossil records in some cases, and so there's not a lot of data in that category. So one of the challenges for the field then has been to understand why we get this anatomical selectivity of extinction that seems to suggest a physiological control. Andy and his colleagues suggested that high PCO2 in ocean acidification would be one way to produce this kind of selectivity. And I think that's a reasonable interpretation. I'll show you by the end of the talk that there are probably some other things going on that also relate to respiration that aren't just about this taxonomic selectivity. And so we've learned a bit about paleontology. We've also learned a lot about geochemistry. And on this front, I've been really fortunate to be able to participate in this work. Thanks to an intellectual infrastructure that started in the late 1980s. And so Wei Jiayong on the top here was a geologist at the Guizhou Geological Survey in Guizhou province of southern China. And he made many of the maps of South China, of Guizhou province in the 1950s, 60s, 70s. And in the late 1980s, he connected partly by accident with, whoops, I'm sorry. Every time I touch this, I end up moving the slides. He ended up connecting with an American geologist, Paul Linus, who actually did his master's at Stanford in the 1960s. So Paul Linus came from the University of Kansas, met up with Wei Jiayong. They were interested in the development of carbonate platforms. The carbonate platforms in South China from the Permian and Triassic are structurally dissected. They're dipping in many cases 60 to 90 degrees. And so you get these geological cross sections of carbonate platforms that are 2 to 3 kilometers thick and are buried in siliciclastics. And so the map view is a geological cross section. And it's absolutely spectacular. Paul is a carbonate sedimentologist. Wei was a mapping geologist. They trained a couple of students, including a geologist, Dan Lehrman, who's at Trinity University in Texas. Dan was one of the advisors to me as I was a graduate student, and Wei helped me when I was in the field in South China. So I was sort of a third generation trainee of this project. When I was in South China, this student here, Li Xiaowei, was a master's student at Guizhou University. He then came to Stanford and did a PhD at Stanford, graduating right before the pandemic started. And so Xiaowei and Fu Hongbin and Katya Meyer and Ellen Schall here have their fingers on the Permian-Triassic boundary in these carbonate platforms in South China. When I was starting graduate school, I emailed Dan Lehrman and ultimately then ended up meeting Paul Linus and Wei Jiayong and said, look, I really love the end-Permian extinction. You guys are building this amazing stratigraphic framework to work within. You know, could I come and do some paleontology and geochemistry within this framework? They were very kind to bring me along, and you know, my career has certainly benefited enormously. I hope that they feel similarly. And so we know a bunch of things now about the environmental changes at the end of the Permian from being able to interrogate these Permian-Triassic stratigraphic sections. One thing that we've learned is that there's a major global warming event that happens at this time, and so you can see here that, if I back up for a second, this Permian-Triassic boundary where Ellen and Katya and Xiaowei and Fu Hongbin have their fingers, if you do a carbon isotope stratigraphy through these strata, there's a big negative carbon isotope excursion sitting right where their fingers are. And that shows up right over here. That carbon isotope excursion coincides with the onset of a major global warming event that occurs across the Permian-Triassic boundary. And so a couple of different research groups have worked on this. The first major paper on this was from Michael Yokimsky and colleagues about a decade ago, getting oxygen isotopes out of conodont microfossils and showing that we get about a 2 per mil shift in the oxygen isotope composition of the conodonts. We think this is an ice-free world, so there's probably not much of an ice melting signature here. And so this equates to something on the order of 10 degrees centigrade warming. This is a massive global warming event coincident with the extinction. And that warming actually appears to persist. So here's the warming event at the boundary. A lot of the early Triassic is very warm for the next 4 or 5 million years. And so there's a very interesting climate problem that I won't go into lots of details about here, but this warming doesn't stop right after the end-Permian extinction. In my lab group, I had seen these data and had been looking at the Permian-Triassic boundary sediments. I was really interested in this acidification story and was curious if we could get geochemical data that might help us test this hypothesis. One isotope system that was starting to be developed at the time I started at Stanford was the calcium isotope system. So taking your limestone, grinding it up, and instead of measuring the carbon isotope ratios, measuring the calcium isotope ratios. And the logic here was that if there was an ocean acidification event, we might expect more calcium delivery to the oceans than calcium burial, because the oceans would be undersaturated with respect to calcium carbonate temporarily. And we found some evidence of that both in the bulk carbonate record, where we seem to get a small negative excursion here. And we went in, Jessica Hinojosa, up in the top right of your screen here, she went in and measured the calcium isotope composition of these conodont microfossils. And again, found a bunch of noise, but a general negative shift across the Permian-Triassic boundary, suggestive of an ocean acidification event. We also think that we see some sedimentary evidence of this. Sorry, my cat is joining the talk for a moment. We think that we see some sedimentary evidence of this as well when we work on these carbonate platforms. So this would have been the same in that photo that I showed you in the field, but the surface was quite weathered. If you look at a fresh surface, you can see the Permian-Triassic extinction contact running across the strata. In this figure, the lower part, the lighter colored part, is a fossil-rich uppermost Permian limestone, and it is immediately overlain and overgrown by this darker, blotchier colored limestone, which is a thrombolytic microbialite that extends for about 10 meters up section. At this surface, we've had some debate with colleagues about whether or not there's any evidence of subaerial exposure and meteoric cementation of the underlying limestone. My collaborators and I don't think that we see any, and that this could be a submarine acidification and dissolution event. We're currently trying to use nanosims to see if we can get in and look for meteoric cements at very fine spatial scales to further test this hypothesis. And then the final piece of the puzzle here is comes from uranium isotopes. And so, certainly when I went through all of my training, I learned about uranium as being a way of doing absolute age dating, thanks to its radioactive decay. It turns out that uranium also fractionates during reduction from uranium-6 to uranium-4. And it turns out that there's uranium dissolved in seawater, and that as seawater becomes anoxic, uranium goes through this reduction reaction in association with organic matter on the seafloor, and that uranium-6 is fairly soluble, uranium-4 is not. And so if you have a lot of seafloor anoxia, you expect to see two things. One thing you expect to see the uranium concentration in seawater decline, because the uranium-6 is being reduced to uranium-4, which is then insoluble and removed from seawater. The second thing you expect is that there's a nuclear volume effect on uranium, which means that the kinetics of uranium-238 reduction are faster than the kinetics of uranium-235 reduction. And so we expect the uranium-238 to end up preferentially reduced into organic matter, leaving seawater isotopically light in uranium. So we're using it more like a stable isotope system than like a radioactive system. And Kimberly Lau, who's now a professor at Penn State, and in fact, the most recent recipient of the Donath Medal from GSA at the GSA meeting earlier this month, she did her PhD developing this uranium isotope record from our samples in South China, co-advised by Kate Maher and me at Stanford. And Kim was able to show that we see both of these things. We see a reduction in uranium concentration across the Permian-Triassic boundary, both in South China and in stratigraphically equivalent carbonates in Turkey. And that at that same time, we see a very dramatic negative shift in the uranium isotope composition of seawater. And that the only way to get that shift plausibly is from a big anoxic event, that if you try to monkey with the riverine flux or the riverine isotope composition, the changes just don't happen fast enough to explain the record that we see. And more recently, with a master's student, Michael Pimentel, we've been doing some Monte Carlo modeling to try to better quantify exactly how much anoxia is required to produce this negative shift in the uranium isotope record, as well as the decline in uranium concentration. And I think for the sake of time, I'll just say that Michael tried out 50,000 different scenarios, changing how long the anoxic event was, how much anoxia there was, and then went through a series of processes that I'd be happy to talk about during the question and answer session to match up his model output with our data in a fair way. The ultimate result of this is that he modeled an enormous range of scenarios, was able to use a principal component analysis to figure out which of those model runs are most similar to the data that we have. And that's this bottom diagram right here. And essentially what it suggests is that you need about 20% of the seafloor to become anoxic, whereas you start with something more like the modern that's much less than 1%. And that amount of anoxia probably declines over the first 1.5 million years after the end-Permian extinction, but remains far above any sort of background level. So there's less anoxia, but still quite a lot of anoxia once we're a million or 1.5 million years after the major extinction event. We also now think that we understand why the extinction event happened, or what the geological cause was, and that's the eruption of the Siberian Traps large igneous province. The Siberian Traps are the largest continental flood basalt province, and so that alone suggests that they would probably have a larger environmental impact than other large igneous provinces. Again, largely at the global scale through gas release, right? That there's clearly a local effect just from all the lava flows. But for a global mass extinction event, the main issue is gas release into the atmosphere, causing climate change and ocean chemistry change. The geological circumstances of Siberian Traps eruptions suggest that they might have been even more environmentally impactful than just sort of a random, very large igneous province. And the reason for that is that they intrude through the Tunguska Basin, which has several kilometers of Neoproterozoic and Paleozoic stratigraphy. And that sedimentary stratigraphy is full of a lot of carbonate rocks, sulfate and sodium evaporite minerals, so gypsum anhydrite, halite. There are petroleum systems in some of this basin, and there's even a large coal deposit near the top of the basin. The hypothesis put forward by Henrik Svensson and colleagues back in the late aughts was that the intrusion of the Siberian Traps not only released gases that inherited from the mantle, but also caused degassing of these sedimentary rocks in the crust through the intrusion of dikes and sills at 1200 to 1300 centigrade into these sedimentary rocks. They even argued that by heating up salt in the presence of petroleum, that you could generate chlorofluorocarbons that would destroy the Earth's ozone layer. It turns out, as an interesting piece of just sort of geopolitics, the Soviets and now the Russians have been well aware of this interaction between the Siberian Traps and the sedimentary crust, because when these interactions happen, you get buildup of gas pressure, and ultimately that gas pressure in some cases exceeds the overburden pressure and blows holes into the crust. So you get these gas explosion structures. As I understand it, sort of the combination of mantle material and potentially hydrocarbons actually leads to some iron reduction. And so you get magnetite ore associated with these gas explosion structures. And so all of the black dots on this map are places where the Soviets and Russians have identified iron ore deposits that are a consequence of the Siberian Traps eruptions. And these are on the scale of, say, a kilometer or so. And in the Svensson paper, if you look it up, they've got a nice photo even of strip mining of one of these deposits. Seth Burgess and colleagues have done some amazing work to get radiometric ages on intrusive and extrusive components of the Siberian Traps. And when they've done that, what they've found is that the extinction horizon right here, dated from the volcanic ash layers, sits right in the middle of the dates on these different units of the Siberian Traps. And so the traps are clearly starting to erupt shortly before the major mass extinction event. They probably peak in intensity somewhere near the extinction interval or very shortly thereafter. And most of the dates of the materials that Seth was able to access sit within 500,000 years of the extinction horizon. The traps are in a quite remote area of Siberia, and so getting access is mostly related to river canyons. There are large areas of the traps that are hard to access and hard to date. So I think that we have a fairly full story here where we can explain these environmental changes from the gas release associated with the intrusion of the Siberian traps, which would have degassed CO2 from the carbonates and the organic matter, as well as sulfur gases and potentially halocarbons from the salts and petroleum. So I wanted to take sort of the later part of my talk to talk a little bit about what we've been doing now to try to connect better the geochemistry and the paleontology, and to say, do these environmental changes really explain the extinction in a way that we can understand? And I think the big challenge has been, for a long time, we've had the fossil record. We've known that there's a big extinction event here. We've tried to use the pattern of extinction to make guesses as to what kind of processes might have caused it. The development of isotope geochemistry and in the more recent development of plasma mass spectrometry, where we can access elements on the periodic table with high precision that we couldn't access before, like these uranium isotope measurements. That's given us better and better insight into what the environmental changes were during the end-Permian extinction. What's happening right now is that some people in the climate modeling and Earth system modeling community, people interested in animal physiology, often doing this work to try to predict the next 100 or a couple hundred years, are seeing that the fossil record can be analyzed, or the geological record can be analyzed using the same tools, and that we can try to actually quantitatively connect the environmental change to extinction, run out different scenarios in the models and see which ones actually match both the geochemical and the paleontological data. And so this has been really fun. In the modern, people are worried about something called the deadly trio in the oceans. And here I'm going to focus on marine biology because that's where we have the best fossil record. It's also where we have the best geochemical constraints on environmental change. The same logic should be able to be applied to the terrestrial fossil record as well. And so we worry about these things in the modern. In the end-Permian, we have good evidence that probably all of these things happened. And Curtis Deutsch and his graduate student, now postdoc Justin Payne, so Curtis on the left, Justin on the right, have developed a simple index for figuring out how good or bad any parcel of water is as habitat for aerobic animals, assuming that at a bare minimum, animals need to be able to breathe if they're going to be able to live. And this, from a biological perspective, it's a fairly simple model. From a geologist perspective, it's awesome because the things that they're using are things we can actually measure in the geological record. And so here's the basic logic. And don't worry too much about the math and symbols. I'll explain it in plain English as well. The key point here is that Curtis and Justin use this logic. They say oxygen supply, or the ability of an organism to take oxygen into its body, is related to its body mass. That's this B to the delta term, and to the oxygen concentration in the environment, right, by some scaling factor. And then they say, okay, the oxygen demand, the amount of oxygen the body needs, is also going to be scaled to body size. And it's then going to be related to temperature. So absolute temperature is T here. KB is just Boltzmann's constant, right? So this is just a constant that's known from physics. And the other biological term here is this E0 term. And this is just telling us how temperature sensitive the organism is. So does its metabolic need change rapidly with temperature or change, or slowly with temperature change? And so what we can do then is we can just take a supply to demand ratio, right? And we know that this ratio needs to be bigger than 1. If it's less than 1, then the organism isn't getting as much oxygen as its body demands, and it just won't be able to live there. So phi is just that supply-demand ratio. And it then becomes related to this A naught, which is just the alpha S over alpha D term. So this is just a constant. It's related to body mass, related to oxygen in the environment, and related to the temperature sensitivity of the organism. And so this is what's super cool, is this hypoxia tolerance and temperature sensitivity. We can find those out by running experiments on animals in the lab. And for things that are extinct, we can run experiments on their close relatives. Oxygen can be determined from geochemistry. So we can go back and find out what oxygen concentrations were like in the geological past. The same is true for temperature. Again, Boltzmann's constant is known. This is just E, right? And we know body size from fossils. And so we actually have a numerical model that can be put into climate models. So this is a model of physiology that we can put into our climate model that has simple enough terms that we can actually determine all of them from the geological record. And so when we're trying to figure out these A naught and E naught, we send our students. This is Kemi Yashingiwa. She's a new PhD student working with me and with Eric Sperling at Stanford. And here she is this summer working with another student at the University of Washington at their Friday Harbor labs, taking brachiopods, sticking them in tanks, and seeing how their respiration responds to temperature and oxygen availability. And from that, we can, basically determine how habitable any given piece of water was. In general, water that has more oxygen, so going up on the vertical axis here, is going to be more viable as habitat for animals than water with very low oxygen. The higher the temperature, the faster all chemical reactions proceed, and so the higher the metabolic rate tends to be. And so given any amount of oxygen, cooler water tends to be more habitable than very hot water. This model is a little bit oversimplified in that at very cold temperatures, there's a little bit of reversal of this effect where the very cold water affects the organism's function in other ways. And so the world doesn't completely get better the colder we get. So we took this model and applied it, and this is definitely the royal we. Justin Penn was the lead author on this study. I contributed, as you'll see in a minute, an analysis of the fossil record to understand how it compared to this climate model. So Justin and Curtis took a climate model run by NCAR. They used an end-Permian paleogeography. They started out with pre-industrial CO2, so in the 180 to 280 ppm range, and then ran the model for 2,000 years, and then ramped up PCO2 to 5,500 ppm and ran the model for another 3,000 years. And so we're seeing in these maps the change in temperature between what appeared to be fairly steady state pre-disturbance value and the late part of the model run where we seem to stabilize after ramping up CO2. And so we can see the climate warms everywhere. It warms more in certain parts of the oceans than in other parts of the ocean. It warms more near the surface than it does at depth. What's cool about this model is the temperature in the model before the disturbance matches end-Permian paleo temperatures. The temperature in the model after the disturbance matches the geochemical record for oxygen. So we think we're doing okay on that front in terms of a realistic climate perturbation. And then the next thing that again, the royal we, meaning Justin, did was to look at oxygen concentrations in surface seawater, which went down. And we can see the deoxygenation was particularly pronounced at high paleo latitudes. At lower paleo latitudes, there was less oxygen loss. And this relates to the biogeochemistry that as you warm the planet, you change the rate of overturning circulation, which changes the delivery of nutrients, and in fact ends up reducing productivity in the tropical surface ocean, which means there's less organic matter sinking through the tropical surface ocean, less oxygen demand for respiration, And so the tropical surface ocean actually doesn't deoxygenate all that much. It warms up a lot, but it doesn't deoxygenate terribly much. And when you look at the model output, the amount of seafloor anoxia before the extinction, before the model perturbation matches the data that we have from uranium isotopes. The amount that we see after the perturbation, again, matches the data that we have from uranium isotopes, suggesting that at least in 2 dimensions, this model is producing the right global average changes. And so that gives us some confidence that the model is producing a world that's at least not obviously wrong for the Permian-Triassic boundary. So then we take this model and we stick organisms with different physiological values, so essentially different A0 and E0 values, into this ocean. And we ask, where can they live before the extinction and where can they live after the extinction? Do they still have habitat available? And essentially what you can see here, the dark colors are sort of the bad areas. The light colors, the light yellows here, are the better areas. And so animals that have tolerance to very low oxygen tend to do better than animals that need a lot of oxygen. And in terms of temperature sensitivity, we see that animals that are very temperature sensitive, in bright red here, do poorly after the extinction. Animals that are not very temperature sensitive do better. Not a big surprise. This warming occurs everywhere and vastly increases the oxygen demand. And so any animal that's less temperature sensitive is going to be less affected by that major warming event. It's also better to tolerate low oxygen, right? That you tend to be able to survive better in the lower Triassic Ocean if you can tolerate lower oxygen concentrations, because that's all that's available to you. And so when we put all of this together, we found something that actually surprised me. Curtis and Justin, in this gray envelope here, found that depending on exactly how you calibrate habitat loss to extinction, that you certainly expect more extinction near the poles, less extinction in the tropics, with some variation in exactly how much that is. When you go and look at the fossil record, I had worked mostly on the tropics, right? So South China was about 10 degrees north of the equator at this time. So it was decimated at the end of the Permian. Not only were the reefs gone, but animal shells are very rare. Diversity is quite low. I had a hard time imagining that the extinction was actually worse at the poles. When I downloaded a community resource called the Paleobiology Database that tries to compile fossil occurrences globally and comprehensively from literature, what we found is, in fact, extinction appears to be systematically higher, both in higher southern latitudes and, to the extent that we have data, in higher northern latitudes. And the tropics did the best. Still not very good, right? This is still a loss of 50% of animal species, or animal genera, I should say. But that's better than the situation closer to the poles. So this was really cool because we didn't have enough data to try to separate the physiology of brachiopods from the physiology of bivalves, but it says that in general, one would expect the extinction to have a latitude gradient, and that in fact tropical animals, because they can migrate, they like warmer, lower oxygen environments. Those are starting to move toward the poles, and so while they might not do well in the tropics, they might be able to survive in the extratropics after the warming event. And that allows us then to do some attribution, right? And so as geologists and geochemists, if I have the uranium isotope tool and I go out and make measurements and I say, oh, look, oxygen went down a lot, therefore the end-Permian extinction is caused by anoxia, that seems reasonable to me. If I have another tool and I go and I measure oxygen isotopes and I say, oh, wow, it warmed up a lot, I guess the end-Permian extinction was caused by warming. Both of those things are actually partly true. It appears that both the warming and the deoxygenation played a role in the decline of habitat. What we can do with the Earth system model is we can show that in the tropics, the big effect on animals is the warming. Oxygen loss is not the big stress. When we go to higher latitudes, the extinction and extirpation, or sort of local loss of populations, is driven by the deoxygenation much more than by the warming, because the oxygen drops very low. And so even though the warming has an effect, the oxygen loss is actually a bigger effect. So this is something new for us. We've never been able to quantitatively separate those warming and deoxygenation effects. So that was very exciting for us. And so I think that what I'll do is basically leave it there. Justin and Curtis have taken this approach to start thinking about the current extinction event. And one of the cool things is that the continental configuration to a first order doesn't matter that much. You get these same kinds of latitude gradients with a modern continental configuration as what you get when you have Pangea. And so that suggests that the end-Permian extinction is a useful way for us to think about the biogeography of future extinctions in a modern, warming, deoxygenating, acidifying ocean. The other thing it suggests, I think, is that we can use the end-Permian extinction intensities as a way of calibrating how much habitat loss in the model is equivalent to an extinction, which is something that's sort of impossible to do if you just take the present and model toward the future. You can quantify how much habitat loss you think is happening in the ocean, but you don't know when that's actually going to lead to collapse of a species and its global extinction. So these ancient events may actually give us a way of better calibrating our model projections for the future. And we know from the fossil record that biodiversity recovery is the slowest process in these global disturbance events, that climate warming takes a while to resolve, but probably that timescale is hundreds of thousands of years under most normal conditions. The biodiversity recovery ranges more into the millions of years. And so hopefully, as you're talking to your non-geologist friends and family members, that maybe the story I've told you maybe can help you talk with them about how as geologists, when we trace those operations which are past, we're not just learning about Earth's past, but we're able to foresee distant events in the course of things. So thanks for your time and attention, and I will look forward to trying to answer your questions.
Okay, I've unmuted ourselves here. Any questions from the audience to start? You need to come up here a little bit towards the front if you don't mind.
Yeah, and I think, Jim, that the microphone that Noel was using earlier will also work if you hand that to people. I think I'll be able to hear them.
Excellent.
Can you hear me all right?
Why don't you take the slides down, Jonathan, and
Yep.
we'll go ahead and get your view up bigger.
Yeah, I was.
There you go.
Okay, I'll bring them back up if I need them to answer a question.
If we need them, that'd be great.
Yeah.
Can you hear me all right?
Yes.
Okay. I was curious about the carbonate sequence where people had their hands on the boundary. And when you showed that, that's what I would call a hard ground.
Yeah.
A hard ground. I'm used to anoxia occurring in the deep oceans, but when I looked at your fossiliferous limestone below that hard ground, it would seem to be that was shallow water.
Yeah.
Where do we find in the modern environment anoxia in shallow waters?
Right. So that's a really good point, and I probably didn't talk about this clearly enough. So you're absolutely right. It's a hard ground. The challenge that we're facing is trying to understand if it's a submarine hard ground versus a hard ground developed from subaerial exposure of the carbonate platform. So that was one of the things that we're still trying to figure out on the sedimentology side. In terms of the anoxia, we're measuring the uranium isotopes in those limestones, and we're seeing that negative excursion. What I didn't have time to explain well enough and failed to explain is The uranium has a long residence time in seawater, and so it's pretty well mixed across the whole ocean. And so the logic of the work that we're doing is that we can measure the uranium isotope composition of the uranium that's substituting into the carbonate crystal lattice, which is the uranium-6, and use that to understand the uranium isotope composition of seawater. So it's indicating anoxia. Is it that anoxia is expanding in the oceans somewhere globally? It is not anoxic in the environment that we're measuring. You're absolutely right. It's a shallow, wind mixed, shallow subtidal environment. It is not locally anoxic. It's probably quite warm, but it is not anoxic at the site of deposition.
Thank you.
Yeah, I have a question.
Yep.
My graduate work. Can you back out plate tectonics that we know, if we know any at that era? Because what some of your curves look like some of my curves, and I had a different explanation, but I like yours better. I like all that. I did chemistry also, but you did a lot more, so that's great.
So I guess what's the question on the plate tectonics? I don't think I completely understood.
Can you back that out? Because if you take the Pacific plate northward, you see a similar trend. Just by moving it into the temperature is changing because you're moving toward the poles.
Right. So the time scale that we're looking at across this extinction event is only tens to hundreds of thousands of years. And so on those timescales, I don't think that we're seeing any noticeable effect from plate tectonics, if that's the question that you're asking. And I apologize if I'm answering.
No, that's a good answer. It perked my interest.
Okay.
I'll come talk to you sometime.
Yep.
Thank you.
Hi, I had a question. I want to make sure I understand the general hypothesis you're presenting.
Yep.
Is your hypothesis that there is a surplus of carbon dioxide vented into the atmosphere? This raised the temperature, and then the lower solubility of oxygen in warm water created the anoxia? Or was it some mechanical mixing process that caused the anoxia?
Yeah, no, thank you for that question. You've stated what I should have stated much better than I did. I need you to consult on my on my next talk. You've got it exactly right. So CO2 released from volcanism causes climate warming. That warming reduces the solubility of oxygen in seawater, and that's the major cause of the deoxygenation of the oceans in the model. What's interesting is that it seems to be sufficient on its own. In earlier work, I had hypothesized that the CO2 release would increase silicate weathering, deliver more nutrients to the oceans, and that you might need some higher productivity to drive the anoxia that we see. In Curtis's model, we don't need that. We don't need an increase in productivity. If anything, his model actually slows down the overturning circulation, and so we get slightly lower productivity in the oceans during the anoxic interval. And so the anoxia is really just a solubility problem as the climate warms.
Can I also ask you, was there an increase in dolomitization at the Permian boundary?
Probably not. So on the carbonate platforms that we work on in South China, there are some thick intervals of dolomite deposited probably, say, 2 million years after the extinction event. It's a little bit unclear how much of that is actually Payne contemporaneous. And so I don't think we know for sure, but there's not any obvious shift to primary dolomite deposition immediately after the extinction event that I'm aware of.
Thank you.
I understand that in some of the Permians, end-Permian rocks and in the Triassic, a good indicator of the anoxia is framboidal pyrite. Have you done any studies on that? I understand it requires TEM analysis.
Yep. Yeah, I haven't worked on that personally. Probably the people who've done the most work on that are Paul Wignall, Richard Twitchett, and David Bond, all in the UK. They've done this quite a bit. That work tends to be done more on siliciclastic sequences. I've worked mostly on carbonate sequences. You're absolutely right that the argument here is that rhomboidal pyrite that forms in the sediment column tends to be large, tends to have large crystals. But if you had euxinic seawater, so if you had anoxic seawater with free hydrogen sulfide, you could actually start to form rhomboidal pyrite in the water column around little bits of organic matter. And the argument is that, you know, those would start to form and then they're pretty dense. And so then they'd sink to the seafloor and you get all these very small pyrite rhomboids if you were really making the rhomboids in the water column. Paul and Rich and David have definitely seen decreases in the sizes of the rhomboids across the Permian-Triassic boundary in Spitsbergen, in Italy, in East Greenland. And so there's definitely some indicators that are suggestive, you know, that's another line of evidence that's more local, right? The nice thing about uranium is that it's quite quantitative if we're interpreting it correctly. The downside is it's a global average. The great thing with the pyrite rhomboid proxy is that that's a very local water column indicator. And so that's going to be, I think, you know, the next generation of model data comparison is going to be not just saying, do we get the average temperature, the average oxygen concentration right, but do we get it right in the right places, right? And that'll really help us understand if the models are doing well or doing poorly.
Good.
Very good.
Has the uranium isotope signal been looked for at the Cenomanian-Turonian boundary anoxic event? And what percentage of the oceans were anoxic for that event?
Yeah, I don't have a Cenomanian-Turonian paper to cite for you offhand. I fear that that's because I'm spending half of my time as an associate dean and not because there aren't any papers.
Okay.
There's definitely, this is a proxy that's taken off in the last 4 or 5 years. And so there's been an explosion of papers. There's work on the end-Permian, work on the end-Triassic, work on the late Ordovician, some more systematic compilations for the very early Paleozoic to try to figure out when oxygen really starts to build up in the oceans. It looks like that may be gradual all the way up to the Devonian, whereas, you know, I was taught that it was right near the Precambrian-Cambrian boundary. So it's been a really cool proxy. I just don't know offhand about the Cenomanian-Turonian, unfortunately.
Excuse me, looks like I have the last question, but when you look at the end-Permian versus today.
Yep.
Now, in the end-Permian, we had the Siberian traps burned up a whole bunch of coal measures, as I understand. And that's what we're doing today. How do those two events compare in volume?
Yep. Yeah, so that's been a challenging one. I've tried a couple of things that I thought were clever, but maybe not correct to get at this. I think that everybody who works on this, I think, would say that for the end-Permian, you probably need at least 5,000 gigatons of carbon burned. For the modern, we've burned on the order of, say, 300 gigatons in the last couple centuries. I think the number for the end-Permian is actually larger than that. I would guess that it's a few tens of thousands of gigatons of carbon. So I think the end-Permian is a much bigger event than the modern in terms of climate, and that it's even much bigger than anything we could get to by year 2300, even on the pessimistic scenarios. You know, being part of a school of sustainability, obviously, I hope that Stanford and many other places will contribute to averting our high emission scenarios over the next couple of decades. But so it's a lot for the end-Permian for sure, and I think that's one of the challenges for these climate models. So I guess the other thing to say is the timescale matters a lot. It really depends on how much of that carbon is emitted in, say, you know, century or millennium timescales, where there are very few geological processes to take it out of the atmosphere, versus if it's emitted gradually over a few 100,000 years, then ocean uptake and silicate weathering can compensate for that, and the climate and ocean chemistry effects are a lot less. And so The challenge is, right, as I imagine everyone in the room knows, those are timescales that are really hard to resolve in the geological record. We probably have to figure that out by analogizing much younger events, figuring out what their distribution of emissions rates are on different timescales, and then modeling that back to the end-Permian. My guess is that the worst century or two of the end-Permian were really, really, really bad, and that's where the extinction comes from, is the worst. The worst part of it on timescales less than 10,000 years. Because the longer you go, the more geological processes start to mitigate those effects.
Yeah. Go ahead.
One more question. Is there any relation with the of the warming with the evaporites and the red beds in the Triassic? And I don't know how the timing works out, but you know what you can say about that?
Yeah. Yeah, I think at least in the lower Triassic, there probably is some relationship. When people run these climate models with very high PCO2, you get very hot and very arid continental interiors in some cases. In a very warm world, you're evaporating more seawater, right? The atmosphere can hold more water. And so somewhere you're increasing precipitation. But as we see in the modern as well, right, you can get real extremes where you get drying in some parts of the continent and then extreme precipitation events in other places. And so, I would say at least for the lower Triassic, I think it's reasonable to think that some of these depositional patterns that we see are related to the climate effects.
Very, very good. I've got a couple of questions from the chat that I put up
Yep.
on the screen here.
Okay.
From John Karachewski, where's a good location to view the Permo-Triassic boundary in North America?
Yeah, that's a tough one. The flooding in the Western US mostly postdates the Permian-Triassic boundary. Eric Sperling and Jim Engel published a paper, must be 2004, 2005, I think, in GSA Bulletin, where they think that they have a deep water Permo-Triassic boundary section in the Dinwiddie Formation, I think in Idaho or Nevada. My guess is that if you went out to the field, it wouldn't look like much. I think that it would look like some dark shale on both sides of the boundary. North America just doesn't have good coverage of the Permian-Triassic boundary interval. And this has actually been a really interesting thing, I think, in the history of paleontology, is that North American paleontologists historically have been skeptics about the end-Permian extinction. If you look at early writings by Dave Raup from the University of Chicago, Michael Foote and Shannon Peters. Shannon was a PhD student with Foote at Chicago and is now at the University of Wisconsin. These are some of the very, very best quantitative paleontologists in the world. By looking at compilations of sediment volume, which often are very North America based, they looked at it and said, look, you have such a drop off in sediment volume. Couldn't the end-Permian extinction just be some sort of sediment artifact where we're missing so much rock record that everything that survives up into the late Permian is gone by the time the rock record picks up well again, and that there's nothing biological happening here? People who've worked outside of North America have generally believed that the end-Permian extinction is a real thing, because if you're in South China on these carbonate platforms, it's very abrupt, and the biostratigraphy tells you that there's minimal time missing from going to the pre-extinction to post-extinction. And in fact, early thinking on mass extinction, so Norm Newell, who was really the first North American geologist to think about mass extinction, and worried that all mass extinction was just a geological record artifact. He was writing about this in the 1950s. Otto Schindewolf in Germany was thinking about the same thing. He was a non-evolutionist, right? So he had some other beliefs about science that probably don't hold up very well. But he did go to the salt ranges in Pakistan, and he looked at the Permian-Triassic boundary interval, and he said, all of these species are gone all of a sudden, but I know that it's not a geological gap because there's a lineage of ammonites that I can see evolving very gradually and continuously right through this interval. And so there can't be any time missing here. This has to be a rapid geological event. he hypothesized that it was a nearby supernova that caused the end-Permian extinction. And so it's one of these really interesting things where Newell, who in many ways was right about lots of things about major extinction events, was wrong about the geological record. Schindewolf, who is totally wrong about evolution, got the end-Permian right because he had the right rocks and could just see that if I can trace a species or two that are evolving gradually through this interval and everybody else is going extinct, it's not a rock record gap, it's something biological. So unfortunately, I don't have anything good in North America. Easiest place to get to is probably the Dolomites in Italy. If you want to go and put your finger on the Permian Triassic boundary in rocks where you can actually see some of the sedimentary changes. If China opens up again, I can give you some GPS coordinates. These aren't touristed places. The geology is amazing, and anyone with a little bit of sedimentary geology background could probably go out with a map and sort of figure out, what we've seen. And I'd be happy to help that out. Right now, I don't think it's easy to get to any of these places, unfortunately.
Very good. Bert Vogler thanks you for an exceptional presentation. By the way, he's a guest from Southern California who wrote me this week about joining us. He saw it in the Pacific section of the AVG announcement on our calendar here. So I was glad to welcome him tonight. John Karachewski, once again, man of many questions. Many of us have a classic geologic background and training. Could you briefly discuss the backgrounds and training of your multidisciplinary students at the School of Sustainability?
Sure. Yeah. So for those of you who haven't followed the Stanford news all the time, and honestly, if I wasn't working for Stanford, I don't think I would. Stanford took so we for many years had a School of Earth, Energy, and Environmental Sciences, right, which ended at the end of August. All of the departments in that school became part of this new School of Sustainability. The School of Sustainability also includes our Department of Civil and Environmental Engineering, which is now joint between the School of Sustainability and the School of Engineering at Stanford. We also now have a Department of Oceans. So these are ocean science and policy people, including a lot of marine biologists at our Hopkins Marine Station. And it includes two new proto departments. They haven't been approved by the university yet, but we're building up two departments on the social science side of sustainability. So saying, when we have policy, how do we use our understanding of human behavior to make policies actually work, right? That when we have evidence-based approaches, how do we make sure they actually get implemented in the world by people? Then we have three different institutes, which you can think of as collections of faculty members that go across the departments. And so this is a way to get faculty members from all of the schools at Stanford and all of the departments within the school in. So we have the Precourt Institute for Energy, the Woods Institute for the Environment, and we will have a new institute focused on sustainable societies. And then in addition to all that, we're also building up something that we're calling an accelerator, which is essentially an arm of the school devoted to taking ideas produced in academia and figuring out how to deploy them at scale quickly, right? And whether that's policy and government or technology and industry, all of those kinds of things, figuring out how do we take what we know and teach our students and make it available to people with the power to do things at much larger scales quickly, because that's been certainly one of the challenges has been taking university-based research innovation and actually making it sometimes it works at very small scale and doesn't work at large scale, or isn't feasible at large scale. We're trying to build that into the research that we're doing at an earlier stage, so that we do things that have application and impact quickly. So in terms of students, what this means is we're hoping that we'll hit, with at least one class, almost all of the undergraduates at Stanford. Any background in engineering, in biology, in math, physics, chemistry, earth sciences, even social sciences. You know, we have people doing law, business, sociology, political science, economics. Our school has all of that in it. It's a new experiment. It's definitely, as I imagine many of you can imagine, putting all these people with really different disciplinary backgrounds in the same room. It isn't always smooth immediately, but people are learning to think differently, right? They're learning to think about, okay, if I have this geological insight, how do I make it useful to my energy engineering colleagues, right? How do I take what I understand about how the climate works and talk with a policy person to figure out, well, which of the things that we can do to ameliorate climate change, which of those can we actually implement quickly? And, you know, whether that's a technology or a policy. So we're learning as we go. You know, it's we're fortunate to have a lot of resources. We are, you know, I think the way that we've thought about this is essentially that, you know, imagine launching a rocket ship and then having, you know, it's partly built and then you've got a bunch of parts in hand and you're trying to build it while it's flying through the atmosphere. That's sort of how we feel at the moment. But we think that we have space for everybody. And I think that's really it, right? Is that, you know, sustainability is a societal challenge. And so everybody is affected by these issues. And fortunately, I think many people have ways that they can participate, you know, at a basic level, just by voting, right? And getting in elected representatives who are going to promote policies that are responsible. But you know, for a group like this one, geological knowledge is the underpinning of all of Earth's resources, right? And so we can't do anything in sustainability space without understanding structural geology, geologic hazards, sea level change, water resources, minerals, you know, subsurface geology, whether it's for responsibly extracting fossil fuels or for putting CO2 back into the ground, right? We need all of that. So I hope that, you know, if any of you have expertise and want to figure out, you know, how to send students our way or how to participate in our programs, you know, drop me a line and I'll be happy to try to figure out how to connect you appropriately. I know you have many Stanford geology speakers coming your way this, you know, in the next few months. So you may not need my help, but I'm happy to try to be useful if I can be.
Thank you. That's a very complex subject, obviously. I hope you guys have a Rubik's Cube for making decisions.
Yeah, we use that with the magic 8 ball, right?
There you go. All right, one final geologic question, then we'll let you go. From Ray Sullivan, interested in the comparison with the environmental events associated with the Deccan traps and the KT boundary. So can you say a few words about that?
Yeah. I mean, the KT is really interesting because we have, you know, in some ways too many suspects for the murder, right? We have a very large crater on the Yucatan Peninsula of Mexico, and we have a large igneous province on the Indian subcontinent. My view, which I think represents the majority of people working on this topic, though not absolute consensus, is that the impact event matters a lot more than the Deccan traps. A couple of reasons for that. You know, on the Deccan side, it's a much smaller large igneous province than the Siberian traps. In addition, it's intruding more into you know, sandstones and I think some igneous basement that aren't going to be as volatile rich as the Tunguska Basin in Siberia. So I think there are a few reasons to think that it wouldn't have emitted, you know, as much gas into the atmosphere as the Siberian traps. When you go into the sedimentary record to look for geochemical fingerprints of Deccan eruptions, you see that the eruptions start maybe 200,000 years before the extinction event. They definitely cause some climate change. They don't do anything dramatic at the moment of the big extinction event. When you go into individual stratigraphic sections and ask where is that very abrupt loss of biodiversity, where you can do that statistically, it always coincides with the impact layer. And so, you know, I think it would be a mistake to say that the Deccan traps do nothing at all. They certainly affect Earth's climate. they may affect biodiversity a little bit. I don't think that you need them to explain most of what you see in the end Cretaceous mass extinction. The other thing that you notice is if you look at the pattern of extinction, a lot of the selectivity patterns that I showed you for the end Permian in terms of animal anatomy and physiology are actually reversed for the end Cretaceous. And my personal sense is that that makes more sense if you have sort of a collapse of photosynthesis and food supply than if you have a mechanism like what the Deccan would do, which presumably would look a lot more like the end-Permian event. You know, the other thing is that, you know, on a very short time scale, I do think the Chicxulub impact is unlike anything else that's happened in the Phanerozoic due to its size, right? The crater is 180 kilometers in diameter. So if I were sitting on one side of it, I think you'd be most of the way to Sacramento by the time you get to the other side of the crater. If you calculate the energy of impact, it's between 100 and 500,000 times larger than the energy of all the nuclear devices that have ever been detonated. It's 1,000 times larger than the world's entire nuclear arsenal. You know, that's a really bad Thursday afternoon. You know, and it comes through the atmosphere in a second or two, right? You know, it punches a hole through the atmosphere, it blows a hole in the crust, it ejects material into the stratosphere, you know, at a scale that the Earth probably certainly hasn't seen since, and probably hadn't seen in a very long time, probably since Precambrian time before that. You know, if you think about throwing a rock into a pond, right, and you get an evacuation of water and then a splash up into the middle, in the numerical models of that end Cretaceous impact, the rock splash of crustal material pierces the tropopause temporarily after this impact event. I mean, I love teaching it. I don't think that I have any way of giving my students a visceral sense of what that impact event was like, right? I mean, it is so large that, you know, we have enough trouble, you know, teaching students about things like the eruption of the Yellowstone caldera, right?
Yeah, right.
Like trying to get students to get a visceral sense of what it would be like to be on the planet when an 8-kilometer asteroid hits it at 20 kilometers per second. You know, I don't know how to explain that. You know, what blows me away is the end-Permian extinction is worse, right? Despite probably not having an impact event like that.
Right. Okay, well, thank you very much. We sure appreciate your time. I owe you a beer sometime.
Sounds great. I would love that.
We'll get together. And our speaker next month, as was alluded to, is another Stanford professor, Dr. Marty Grove. He'll be here in person. So we're going to have an in-person speaker for the first time in a long time, which we appreciate as well. So again, thank you, Jonathan.
Great to see you all. Good to see you, Noel.
Bye now.
Bye-bye.
Night. Okay. Hi, Ray.
How are you?
Good. How are you doing?
Pretty good.
Good.
I enjoyed the talk.